Hi there. Some time ago I constructed a CNC table for my manual lathe. This has proved to be an excellent tool. One thing that's been lacking is the ability to perform thread cutting and other spindle synchronized operations. For these types of operations, a spindle encoder is required. So in this video, I'll show how I went about building a spindle encoder for my lathe. After some head scratching, I decided to create a belt-driven system with a feed directly off of the spindle. There's about 12 millimeters of thread exposed on the spindle, so I'll make a gear that will screw onto the spindle with a locking nut to prevent the gear from unscrewing itself. The encoder's backplate will be fixed to the lathe and will allow for belt tension adjustment. A 200 tooth MXL tooth belt will be used to couple the spindle gear to the encoder gear. There are 8 different components in this design. The 114 tooth gears will be 3D printed before being fitted to the machine gear cores. 2 bearings will support the encoder shaft. The encoder gear will be clamp fitted to the encoder shaft with a wave washer providing bearing preload. A CUI AMT 102 encoder is used. This encoder has quadrature and index outputs, which should make it ideal for this application. The first component to manufacture is the spindle gear core and lock nut. So over on the lathe, we start with a facing operation on a piece of 70mm 6082T bar stock. We turn the different ODs and face the backside of what will become the lock nut. After checking dimensions, we chamfer the edges. Next up, we drill an 8mm hole before taking a second pass with a 12mm drill bit. We then bore the center hole to 48.4mm in preparation for the threading operation. After a quick check with the bore gauge, we're ready to part off the component. This alloy is not particularly great for parting off as it has a tendency to gall to the parting blade. WD-40 helps to reduce the amount of galling, but care is needed nevertheless. We then mount the parted off component in the 4-jaw chuck. After dialing in, we start with the threading operation. Threading on a manual lathe works very well, however it's a time-consuming operation. Firstly, my lathe requires that 3 gears are swapped out. A number of levers then have to be positioned for the required thread pitch. For harder materials, I would normally fit the compound slide and set it to 29.5 degrees. All of this takes at least 15 minutes. Then there's the problem of ensuring that the half nuts are engaged in the correct sector. Finally, there's the problem of threading towards the face. A great deal of concentration is needed for this, as you have very little time to disengage the half nuts before the tool crashes into the face. All of these were drivers for this project, as none of these are problems in a CNC system. With the threading complete, it's time for a trial fitment on the lathe spindle. The fitment is a bit loose, but as I don't have an M50 by 1.5 go no-go gauge, I went a little deeper on the threads than normal just to be safe. Over on the mill, 2 5mm holes were drilled on the flange. These holes will be used for fastening the lock nut with a key spanner. The core was then parted off from the lock nut before press fitting the 3D printed gear to the core. Next up is the backplate. A piece of scrap 5mm aluminium plate was mounted to the bed of the small CNC milling machine. The tool height is set automatically using a height gauge. After center drilling the hole locations, the holes were drilled to size. A slot was then milled to facilitate belt adjustment. The perimeter of the backplate was then milled. The holes for mounting the encoder and encoder gear spacer need to be positioned very accurately, so it's over to the manual mill for the next operations. After dialing in the backplate using the spindle hole, the encoder and spacer holes were center drilled. The encoder mounting holes were drilled to 2.5 mm. The encoder spacer holes were drilled to 6 mm. The center hole was drilled to 12 mm before taking it to 16.5 mm using a boring head. The encoder spacer's 6 mm holes were then countersunk. Finally, the 2.5 mm holes were tapped to M3. Next up is the encoder spacer. This was machined from a 50 mm piece of aluminium bar stock. After facing and turning, the OD was chamfered. A 12 mm hole was then drilled the entire length of the component. The hole was then bored to 16 mm. The bearing recess was then bored to 21 mm. A quick check with the hole gauge and we're good to go. After chamfering the recess, it was time to part off the component. The 4-jar chuck was then fitted. The component was fitted backside out and dialed in using the OD. The bearing recess was then bored to size. The recess was then chamfered. Over on the manual mill, the component was centered. After center drilling, 3 holes were drilled with a 5 mm drill bit. To complete the component, the 3 holes were tapped to M6. Next up was the shaft. This component was fabricated from a piece of 12 mm hardened and ground shaft. At 53 Rockwell C, a hacksaw was unable to cut it, so an angle grinder was used to cut off a piece. On the lathe, after facing, an 8 mm OD section was turned. My reground carbide insets had no problems with this very hard material. After confirming that the OD was good, the edges were chamfered. The other end of the shaft was then faced and chamfered. The next component to be manufactured is a small shaft retaining ring. This will be fixed to the shaft with Loctite retaining compound and will prevent the shaft from moving axially. A 60mm piece of mild steel is faced and turned to 15.5mm OD. The hole was drilled to 11mm. The ID was then bored to 12mm. The ring was then parted off. The final component to manufacture is the encoder gear core. This was manufactured from a 60mm piece of aluminium bar stock. Over on the lathe we face and turn the different ODs. A center pilot hole is then drilled before taking it out to 11mm. The center hole was then brought to size. The edges were then chamfered before parting off the component. The part was then turned around in the lathe and the backside faced to length. To allow the core to clamp to the shaft, we need to machine a couple of slits on the part, so it was over to the mill to perform the first slitting operation. The part was then mounted vertically in order to machine the second slit. The slit had to be finished off with a hacksaw, as the slitting saw had too large an OD to cut the entire slit without touching the back of the bore. A counter bore was then milled to accommodate the head of the clamping bolt. After center drilling the hole at the base of the counter bore, a 3.3mm through hole was drilled. A 4mm end mill was then used to bore the hole to the slit. Over at the vise, the 3.3mm hole was hand tapped to M4. We can now assemble the different components. The encoder can now be fitted. The encoder kit comes with this spanner-like device, which is used to ensure the correct spacing between the mounting surface and the shaft insert. The insert rests on the surface of the tool before press fitting the collar onto the insert using another tool provided in the kit. We can now screw the encoder onto the back plate using the two M3 button head screws. So we can now fit the parts to the lathe and give it a trial run. After wiring the encoder to the CNC controller, it was time to configure Linuxcnc. This was really quite straightforward. 3 new inputs were added, 2 quadrature inputs and the Z or index input. Only a few additional lines of code were required in the HAL file for the new inputs. I also added a low-pass filter in the configuration to reduce the possibility of electrical noise from interfering with the 5-volt signals from the encoder. Finally, a rev counter was added to the PY VCP panel. We can now do a quick test at various RPMs, starting at 70 RPM. We then go to 470. Then to 1255. And finally 2000 RPM. With the spindle encoder complete, it was time for a trial run. A simple threaded rod was designed in Fusion 360. The rod has a M10 by 1.5mm threaded section. On the lathe, the CNC table was mounted. With a 12mm XC45 carbon steel bar mounted in the chuck, it was time to go. The first operation was a simple facing operation. Next up, the OD was turned to the desired dimensions. For the threading operation, I handcrafted the G76 code, as there were some issues with the Linuxcnc turning post processor. As this was a first attempt, I kept the cuts quite shallow. I also set the Q parameter to 29.5 degrees to lower the cutting forces on the tool. With the threading cut, a quick check was made with an M10 by 1.5mm nut. Not bad at all. The nut is a little bit loose, so I could probably have gone a bit shallower on the threads. Nevertheless, I'm very pleased with that for a first attempt. So thank you for watching. If you enjoyed this video, please like and subscribe.